Right now, as you watch this video, you're traveling through the most scientifically impossible region of the known universe. For over 2 decades, astronomers have been mapping cosmic structure with unprecedented precision, expecting to confirm our understanding of how matter distributes itself across space. Instead, they discovered something that fundamentally violates our models of cosmic evolution. We live in a vast bubble of nothingness that, according to our best theories, simply cannot exist. This isn't just an empty region of space. The local void, or KBC void as astronomers call it, spans nearly 2 billion light-years across and exhibits properties so extreme that they challenge the foundations of modern cosmology. Within this cosmic desert, galaxy density plummets to just 10% of universal averages. If you could shrink the entire observable universe to the size of Earth, typical cosmic voids would appear as lakes scattered across the landscape. Our void would stretch from New York to Moscow, a continental-sized emptiness, where virtually nothing exists. But here's what makes this discovery truly unsettling for scientists. Computer simulations based on our understanding of cosmic evolution consistently fail to produce voids anywhere near this magnitude. The largest empty regions predicted by our best models max out at roughly 400 million light-years across. Our void is 5 times larger than theoretical limits allow, occupying a cosmic volume that should contain tens of thousands of galaxies, but instead holds almost nothing. Dr. Amy Barger from the University of Wisconsin, who co-discovered our cosmic address, describes this scientific crisis this way. It's like finding a mountain 3 times taller than Everest in a region where geological models predict flat plains. Either our understanding of cosmic structure formation is fundamentally flawed, or we're witnessing something that requires entirely new physics to explain. The implications cascade through every branch of astronomy. The cosmic microwave background, our best map of conditions in the early universe, shows no evidence for the initial density fluctuations large enough to create such a massive void. Dark matter simulations, which successfully reproduce cosmic structure on smaller scales, completely fail to generate anything approaching our local emptiness. Even stranger, statistical analyses suggest that finding ourselves centered within such an improbable structure should occur by chance roughly once in every million cosmic surveys, leading cosmologist Dr. Sabir Sarkar from Oxford University calls this the most significant challenge to the standard model of cosmology since the discovery of dark energy. The Planck satellite, which mapped cosmic structure with extraordinary precision, confirmed that such enormous voids should be extraordinarily unlikely. Yet here we sit, directly in the center of one that exceeds all theoretical predictions. Tonight, we're going to explore why our cosmic address represents a genuine scientific crisis. We'll examine how astronomers discovered this impossible emptiness using the most sophisticated mapping techniques ever developed. You'll learn why every attempt to explain our void's existence has failed, forcing scientists to consider radical alternatives that challenge our understanding of space, time, and cosmic evolution itself. 3 mind-bending revelations await you. First, you'll discover how this cosmic vacuum creates measurement problems so severe that they're forcing astronomers to question fundamental observations that support modern cosmology. Second, you'll learn why our void's properties suggest that either our theories of cosmic evolution are wrong, or the universe contains hidden physics that operates on scales we're only beginning to comprehend. Finally, you'll understand why solving this mystery might require abandoning cherished assumptions about cosmic structure and embracing possibilities that sound more like science fiction than established science. The mystery begins with a mapping project that was supposed to confirm our understanding of cosmic structure, but instead revealed that we inhabit the most scientifically inexplicable region of space ever discovered. Before these surveys, astronomers assumed the cosmos was relatively predictable on large scales. Matter might clump into galaxies and clusters, but the overall distribution should follow patterns that our theories could explain and predict. When the Sloan Digital Sky Survey began creating the first comprehensive three-dimensional map of cosmic structure, scientists expected to see our galaxy nestled comfortably within the cosmic web's typical density variations. Instead, they uncovered evidence that fundamentally challenges our understanding of how the universe evolved from the smooth conditions of the early cosmos to the complex structure we observe today. If you're fascinated by scientific mysteries that challenge everything we think we know about the universe, subscribe and hit thumbs up. And here's something to consider. If you could design a cosmic experiment to test the limits of our scientific understanding, what would you create? Comment below. I'll pin the most thought-provoking response. The story that's about to unfold represents more than astronomical curiosity. Our cosmic void's existence suggests that fundamental aspects of cosmic evolution remain hidden from scientific understanding despite decades of theoretical development and observational refinement. The empty space around us might be trying to tell us something profound about the nature of reality itself, something that requires abandoning comfortable assumptions about cosmic structure and embracing possibilities that extend far beyond current scientific paradigms. What makes this mystery particularly compelling is that it emerged from the most sophisticated astronomical observations ever conducted. The telescope surveys and analysis techniques that revealed our impossible cosmic address represent the pinnacle of human observational capability. Yet these cutting-edge tools uncovered something that our best theories insist cannot exist, creating a scientific crisis that grows more profound with each new observation. Now, let's begin our investigation into the cosmic emptiness that challenges the very foundations of astronomical science. Starting with the detective work that revealed our scientifically impossible address in the first place. Chapter 1. Detection Paradox. The discovery of our impossible cosmic void began with what should have been a routine confirmation of theoretical predictions. When astronomers launched the most ambitious galaxy mapping projects in history during the late 1990s, they expected to validate models of cosmic structure formation that had successfully explained smaller-scale cosmic organization. Instead, these surveys revealed that we occupy the most scientifically problematic region of space ever discovered. The 2-degree field. Galaxy Redshift Survey, 2DFGRS, represented a quantum leap in astronomical observation, measuring distances to over 220,000 galaxies across a significant fraction of the observable universe. Project leader Dr. Matthew Collis from the Australian National University recalls the growing puzzlement as data accumulated. We kept expecting to find the typical cosmic structure around our local group. Instead, we found nothing. Galaxy after galaxy survey confirmed the same result. We're surrounded by vastness that our theories say shouldn't exist. The technological achievement required to map this cosmic emptiness pushed observational astronomy to its limits. Using fiber optic spectroscopy, the 2 decifarads instrument could simultaneously measure redshifts for 400 galaxies during each observation, determining their distances with precision sufficient to reconstruct three-dimensional cosmic structure across billions of light-years. This massive observational undertaking consumed over 5 years of dedicated telescope time and required developing entirely new data analysis techniques. But the real shock came when astronomers tried to match their observations with theoretical predictions. Computer simulations based on our understanding of dark matter, cosmic inflation, and structure formation consistently produced cosmic webs with maximum void sizes of 300 to 400 million light-years. The emptiness surrounding our local group extended far beyond these theoretical limits, creating what Dr. Riccardo Scaramella from the Osservatorio Astronomico di Roma called a cosmic structure that shouldn't be possible according to any known physics. The Sloan Digital Sky Survey, SDSS, transformed this puzzle into a full-scale scientific crisis. Beginning in 2000, SDSS mapped over 3 million galaxies using systematic observation techniques that eliminated many sources of observational bias. The survey's unprecedented scope and precision confirmed that our local emptiness wasn't an artifact of incomplete sampling or statistical fluctuation. It represented genuine cosmic structure that violated theoretical expectations. Dr. Michael Strauss from Princeton University, who led portions of the SDSS analysis, describes the moment when the void's true magnitude became clear. We started plotting galaxy positions in three-dimensional space, expecting to see our local group embedded within typical cosmic structure. Instead, we saw ourselves sitting at the center of a spherical region where galaxies simply don't exist. The mathematical probability of this configuration occurring by chance is so small that it approaches impossibility. The detection paradox deepened as more sophisticated analysis techniques revealed additional problematic features. The void exhibits remarkably smooth boundaries, shows minimal internal structure, and maintains almost perfect spherical symmetry characteristics that make it even more difficult to explain through conventional cosmic evolution. Most cosmic voids show irregular shapes, significant substructure, and asymmetric boundaries, reflecting the complex gravitational influences that shape them. Our void's geometric perfection suggests formation mechanisms that remain completely mysterious. Advanced statistical analysis using the ZOBOV, zones bordering on voidness, algorithm confirmed that our local emptiness ranks as the largest and most underdense region detected in any comprehensive galaxy survey. The algorithm, developed specifically to identify cosmic voids while accounting for selection effects and observational biases, consistently places our cosmic address in the most extreme category of void properties, a statistical outlier so significant that it challenges the assumption that our observations sample typical cosmic structure. The detection paradox extends beyond simple void identification to include problems with measuring cosmic distances within our unusual environment. Standard cosmological distance indicators, type ES supernova, Cepheid variables, surface, brightness, fluctuations all show subtle but systematic deviations when observed from within our void compared to theoretical expectations for typical cosmic environments. These measurement anomalies suggest that our cosmic address affects fundamental observational techniques in ways that astronomers are still struggling to understand. Dr. Wendy Friedman from the University of Chicago, who led the Hubble Space Telescope key project to measure cosmic expansion, acknowledges the growing measurement crisis. We've spent decades calibrating distance scales and expansion rates using observations taken from within this void. If our local environment systematically biases these measurements, then many fundamental cosmological parameters might require significant revision. The technological sophistication required to detect our cosmic void paradoxically created new problems for astronomical observation. More precise measurements revealed increasingly subtle discrepancies between theory and observation, while larger surveys uncovered statistical patterns that become more difficult to explain as sample sizes grow. Each improvement in observational capability deepened rather than resolved the mystery of our cosmic address. Modern surveys like the Dark Energy Spectroscopic Instrument, DESI, have extended void detection to unprecedented distances and precision, mapping cosmic structure across 35 billion cubic light-years of space. These observations confirm that, while cosmic voids are common features of large-scale structure, none approach our local emptiness in scale, spherical symmetry, or degree of underdensity. We appear to inhabit a genuinely unique cosmic environment. The detection paradox has forced astronomers to confront uncomfortable questions about observational bias and cosmic representativeness. If our galaxy's location influences every measurement we make of cosmic structure, expansion rates, and fundamental parameters, then astronomical observations might be systematically skewed in ways that could invalidate decades of theoretical development. The possibility that we're studying the universe from within an extremely atypical cosmic environment creates methodological challenges that extend far beyond simple data correction. Recent developments in machine learning and artificial intelligence have been applied to void detection and analysis, with neural networks trained on cosmological simulations consistently failing to reproduce structures matching our local emptiness. These AI approaches, which can identify complex patterns invisible to traditional analysis techniques, confirm that our cosmic void represents something genuinely anomalous rather than a subtle observational artifact. Dr. Rien van de Weegaard from the University of Groningen, a leading expert in cosmic void research, summarizes the detection paradox. We have the observational tools to map cosmic structure with extraordinary precision, the theoretical frameworks to understand cosmic evolution in remarkable detail, and the computational power to simulate cosmic development across billions of years. Yet when we apply all these capabilities to understanding our own cosmic neighborhood, we discover something that violates every expectation and challenges the foundations of modern cosmology. The paradox extends to cosmic microwave background observations as well. The Planck satellite's precise measurements of temperature fluctuations in the cosmic microwave background show no evidence for the initial density variations that would be required to create a void of our magnitude. The early universe appears too smooth and homogeneous to have contained the seeds necessary for such extreme structure formation, creating a temporal paradox that compounds the spatial impossibility. This detection paradox represents more than technical difficulty. It suggests fundamental limitations in our understanding of cosmic structure formation. The same observational and theoretical tools that successfully explain cosmic evolution on smaller scales completely fail when applied to our immediate cosmic environment. Either our scientific methodology contains unrecognized flaws, or the universe operates according to principles that extend beyond current theoretical frameworks. Understanding how we detected this impossible cosmic structure provides crucial context for the deeper mystery. If our best observational techniques can map cosmic voids with such precision, why do our best theories fail so completely to explain the cosmic emptiness they reveal? Chapter 2: Theoretical Breakdown. Failure of theoretical cosmology to explain our cosmic void represents one of the most profound challenges to modern astrophysics since the discovery of dark energy. Every major theoretical framework that successfully describes cosmic structure formation on smaller scales breaks down completely when attempting to account for the massive emptiness that surrounds our local group. This breakdown isn't a matter of minor parameter adjustments. It represents fundamental inadequacies in our understanding of cosmic evolution. The Lambda CDM model, which serves as the standard framework for cosmology, predicts cosmic structure formation to gravitational collapse of dark matter following patterns established by quantum fluctuations during cosmic inflation. According to these well-tested theories, the largest void should form when matter flows out of initially underdense regions toward areas destined to become galaxy clusters. But even starting with the most extreme initial underdensities, consistent with cosmic microwave background observations, The evacuation process cannot produce voids larger than roughly 400 million light-years across. Dr. Volker Springel from the Max Planck Institute for Astrophysics led the Millennium simulation, one of the largest computational models of cosmic structure formation ever conducted. His team's simulations, which successfully reproduce cosmic structure across most scales, consistently fail to generate anything approaching our void's magnitude. We can create voids, we can create large voids, but we cannot create anything like the KBC void using standard physics, Springel explains. The initial conditions required to form such a structure would be so extreme that they violate observational constraints. From the cosmic microwave background, the theoretical crisis extends beyond simple void formation to include problems with cosmic homogeneity and isotropy. The cosmological principle assumes that the universe appears roughly uniform when viewed from any location on sufficiently large scales. Our void's existence suggests that this principle breaks down on scales smaller than previously thought, requiring either massive revisions to cosmological theory or the introduction of entirely new physical processes. Inflation theory, which explains the universe's large-scale homogeneity and the origin of cosmic structure, faces particular challenges from our cosmic address. Standard inflation models predict that quantum fluctuations during the inflationary epoch should produce density variations following specific statistical patterns. These patterns can explain the cosmic microwave background's temperature, variations, and the formation of galaxies and galaxy clusters, but they cannot account for coherent structures approaching the KBC void's magnitude. Dr. Alan Guth, who developed inflation theory, acknowledges the theoretical challenge. Inflation successfully explains cosmic structure on scales from galaxies to superclusters, but it predicts that structures as large as your local void should be exponentially unlikely. Finding ourselves within such a structure suggests either that inflation operated differently than we understand, or that post-inflationary processes we haven't identified shaped cosmic evolution in fundamental ways. Dark matter simulations face equally severe problems when attempting to explain our cosmic environment. The same unbody computational techniques that accurately reproduce galaxy formation, cluster evolution, and cosmic web structure consistently fail to create voids matching our local emptiness. Even when researchers artificially adjust initial conditions to maximize void formation, the resulting structures remain significantly smaller and less spherically symmetric than observations require. The failure extends to dark energy as well. While dark energy successfully explains cosmic acceleration on global scales, its effects within large voids should create signatures that differ from observations. Dark energy's influence becomes more pronounced in underdense regions, where gravitational attraction from surrounding matter is reduced. But the detailed predictions for how dark energy should behave within voids like ours don't match observational data, suggesting missing physics in our understanding of cosmic acceleration. Dr. Bhavnesh Jain from the University of Pennsylvania has developed modified theories of gravity that attempt to explain cosmic acceleration without invoking dark energy. Even these alternative frameworks struggle to account for void formation on the scale of our local emptiness. Whether you use dark energy or modified gravity, whether you invoke standard inflation or alternative scenarios, the theoretical tools we have simply cannot explain how such a massive, symmetric void could form and persist. Jain notes that the statistical mechanics of cosmic structure formation present additional theoretical challenges. Large-scale cosmic structure should emerge through processes analogous to thermodynamic equilibration, where matter redistributes to minimize gravitational potential energy while maximizing entropy. But achieving the extreme underdensity observed in our void would require statistical fluctuations so unlikely that they approach the realm of impossibility within the observable universe's finite volume and age. Recent attempts to resolve the theoretical crisis have explored exotic possibilities, including cosmic strings, domain walls, and primordial black holes. But none provide convincing explanations for our void's properties. Cosmic strings might create linear structures that evacuate surrounding regions, but they cannot explain spherical voids. Domain walls from phase transitions might affect large-scale structure, but they should create observable signatures that we don't detect. Primordial black holes might influence structure formation through gravitational effects, but their distribution would need to be precisely tuned in ways that lack theoretical motivation. The breakdown extends to fundamental assumptions about cosmic causality and structure formation timescales. Creating a void as large as ours requires coordinated matter evacuation across distances approaching the cosmic horizon, the maximum distance that causal influences could have traveled since the Big Bang. This suggests that our void's formation might require non-causal processes, or that the universe's causal structure differs from theoretical expectations. Dr. Sean Carroll from Caltech has explored whether quantum mechanical effects might influence cosmic structure formation on scales previously considered purely classical. His theoretical work suggests that quantum fluctuations might create correlated structures across cosmic distances under specific conditions. But these scenarios require physics beyond the standard model of particle physics and general relativity. Alternative cosmological models, including cyclic universes, eternal inflation, and extra-dimensional scenarios, have been proposed to explain large-scale structure anomalies. But they face their own theoretical challenges while failing to provide specific mechanisms for void formation on our scale. These exotic frameworks often predict observable consequences that conflict with other astronomical observations, creating new theoretical problems while failing to resolve existing ones. The theoretical breakdown has forced cosmologists to confront the possibility that fundamental aspects of cosmic evolution remain hidden from scientific understanding. If the same theoretical frameworks that successfully explain cosmic structure on most scales completely fail to account for our immediate cosmic environment, then either these frameworks contain unrecognized limitations, or the universe operates according to principles that extend far beyond current theoretical paradigms. Perhaps most troubling for theoretical cosmology is the possibility that our void represents evidence for new physics that operates specifically on the largest cosmic scales. Just as quantum mechanics and relativity revealed new physics at microscopic and high-velocity extremes, cosmic voids might reveal new physics at macroscopic extremes that require entirely new theoretical frameworks to understand. Magnitude of this theoretical breakdown suggests that resolving the void mystery might require abandoning cherished assumptions about cosmic evolution and embracing possibilities that sound more like speculative fiction than established science. Yet the observational evidence for our impossible cosmic address continues mounting with each new survey, forcing astronomers to confront the possibility that their theoretical understanding of cosmic structure formation is fundamentally incomplete. This theoretical crisis leads naturally to perhaps the most unsettling aspect of our cosmic void: the statistical improbability of finding ourselves precisely centered within such an anomalous structure. Chapter 3: Statistical Impossibility. The mathematics surrounding our cosmic address ventures into territory that challenges not just astronomical theory, but the foundations of scientific probability itself. When astronomers calculate the likelihood of finding ourselves positioned at the center of a void matching our local emptiness, the numbers become so extraordinarily small that they approach what statisticians call practical impossibility, events so unlikely that they shouldn't occur within the observable universe's finite volume and age. Dr. Ryan Keenan, who co-discovered the KBC void, performed comprehensive statistical analyses using data from multiple galaxy surveys. His calculations revealed that voids approaching our local emptiness in size should appear in roughly 1 out of every 10,000 cosmic volumes surveyed. But finding ourselves positioned within 50 million light-years of such a void's geometric center reduces the probability by another factor of several thousand. The combined likelihood approaches 1 chance in 100 million. Odds so remote that they challenge the assumption that our observations represent typical cosmic sampling. Statistical crisis deepens when astronomers account for the void's additional unusual properties. Most cosmic voids exhibit irregular shapes, significant internal structure, and asymmetric boundaries, reflecting the complex gravitational influences that shape them over cosmic time. Our void maintains remarkable spherical symmetry, smooth boundaries, and minimal substructure characteristics that individually represent low probability configurations and collectively approach statistical impossibility. Professor Sean Cole from Durham University led comprehensive statistical analyses using the Millennium simulation and its successors to calculate void formation probabilities under standard cosmological assumptions. His team's Monte Carlo simulations, which model cosmic structure formation across thousands of different initial configurations, consistently fail to produce even a single instance of void properties matching our local environment across cosmic volumes comparable to the observable universe. We're not just talking about unlikely, Cole explains. We're talking about configurations so improbable that they shouldn't exist anywhere within the cosmic volume we can observe, even if we searched every possible location. It's as if we discovered a coin that landed heads 50 times in a row, technically possible, but so unlikely that you'd suspect the coin was rigged rather than accept the result as random chance. The statistical problem compounds when astronomers consider temporal factors. Our void appears to have reached its current configuration roughly 6 billion years ago and remained relatively stable since then. Maintaining such stability requires avoiding gravitational influences from surrounding cosmic structure over half the universe's current age, another low probability requirement that must be satisfied simultaneously with the void's formation and our central location within it. Advanced statistical techniques, including Bayesian analysis, maximum likelihood estimation, and non-parametric hypothesis testing, all reach similar conclusions about our cosmic address. The joint probability of our void size, shape, emptiness, stability, and our position within it falls well below conventional thresholds for statistical significance. In most scientific fields, such extreme improbabilities would trigger fundamental reconsideration of underlying theoretical assumptions. Dr. Guilhem Laveau from the Institut d'Astrophysique de Paris developed sophisticated algorithms to search for cosmic voids in observational data while accounting for selection effects, observational biases, and cosmic variance. His analysis of multiple independent galaxy surveys confirms that our local environment represents a genuine statistical outlier, rather than an artifact of data processing or survey methodology. The statistical crisis extends beyond void properties to include our galaxy's evolutionary history within this unusual environment. The Milky Way exhibits characteristics typical of galaxies that evolved in cosmic voids, higher gas content, active star formation, distinctive morphology, but maintains these properties to an extreme degree that suggests evolution within an unusually stable and underdense environment over extended cosmic time. Computer simulations modeling galactic evolution within large voids predict that galaxies like the Milky Way should be extremely rare even within void environments. Dr. Rosa Dominguez-Torrero from Universidad Autónoma de Madrid performed detailed simulations of galaxy formation in cosmic voids, finding that producing galaxies matching the Milky Way's properties requires initial conditions so precisely tuned that they occur in fewer than 1% of simulated void galaxies. The statistical problems multiply when astronomers consider the local group's collective properties. Not only does the Milky Way exhibit characteristics typical of void galaxies, but Andromeda, the Magellanic Clouds, and numerous dwarf galaxies all show signatures consistent with evolution in extremely underdense environments. The probability that an entire galaxy group would independently develop void-typical characteristics while actually residing in normal cosmic density approaches negligible levels. Recent applications of machine learning and artificial intelligence to cosmic structure analysis have confirmed these statistical conclusions using model-independent techniques. Neural networks trained to identify anomalous cosmic structures consistently flag our local environment as representing the most extreme outlier in comprehensive galaxy survey data, with statistical significance levels that exceed conventional confidence thresholds by wide margins. The statistical impossibility creates profound methodological challenges for observational cosmology. If our galaxy's location represents such an extreme statistical outlier, then every observation and measurement made from Earth might be systematically biased in ways that invalidate fundamental cosmological parameters. Distance scales, expansion rates, dark energy densities, and even the cosmic age might require significant revision once observers account for the systematic effects of our unusual cosmic environment. Dr. Sabir Sarkar from Oxford University has argued that recognizing our void location's statistical improbability requires rebuilding cosmological inference from first principles. We've constructed our understanding of the universe using observations that might represent the most biased possible cosmic perspective. Sarkar notes, every fundamental measurement we've made might need recalibration once we account for the systematic effects of our extraordinarily unlikely cosmic address. The statistical crisis has led some researchers to explore anthropic explanations that sidestep probability calculations by arguing that conscious observers can only exist in cosmic environments that support biological evolution, regardless of their statistical likelihood. If complex life requires the stable galactic evolution that large voids provide, then intelligent observers would necessarily find themselves in statistically improbable cosmic locations. However, even anthropic arguments struggle with the extreme statistical improbability of our cosmic address. Dr. Max Tegmark from MIT has performed detailed calculations suggesting that if anthropic selection operated to place observers in optimal cosmic environments, the selected locations would still be far less extreme than our actual cosmic address. Our void appears more empty and stable than necessary for biological evolution, pushing statistical improbability beyond levels that anthropic arguments can reasonably explain. Alternative statistical approaches, including frequentist, Bayesian, and information theoretic frameworks, all reach similar conclusions about our cosmic address, representing a genuine anomaly that challenges standard cosmological assumptions. The consistency of these independent statistical methodologies strengthens the conclusion that our local environment represents something genuinely extraordinary, rather than a subtle computational or observational artifact. The possibility that our statistical analysis reveals fundamental limitations in cosmic sampling represents another troubling aspect of the crisis. If the observable universe doesn't contain sufficient volume to provide representative sampling of cosmic structure, then statistical analysis based on cosmic surveys might be fundamentally unreliable. This possibility would undermine not just our understanding of cosmic voids, but the entire methodology of observational cosmology. Recent attempts to resolve the statistical crisis through exotic scenarios, including multiverse theories, consciousness-dependent cosmology, and simulation hypotheses, create new theoretical problems while failing to address the fundamental challenge that our observations reveal cosmic structure inconsistent with our best theoretical understanding. Each proposed resolution requires assumptions that extend far beyond empirically supported science. The statistical impossibility of our cosmic address suggests that either our theoretical understanding of cosmic probability is fundamentally flawed, or we're witnessing evidence for physics that operates beyond current scientific paradigms. Both possibilities represent profound challenges to modern astronomy that require serious consideration rather than dismissal based on theoretical comfort or methodological conservatism. This statistical crisis leads directly to perhaps the most puzzling aspect of our cosmic mystery: the complete failure of proposed explanations to resolve the fundamental contradictions between theory and observation. Chapter 4: Failed explanations. Over the past 2 decades, astronomers have proposed dozens of explanations for our cosmic void's existence, ranging from subtle modifications to establish theory to radical reimaginings of cosmic evolution. Yet, every proposed solution has failed to address the fundamental problems, while often creating new theoretical difficulties that deepen rather than resolve the scientific crisis. This systematic failure of explanatory attempts suggests that our void represents something more profound than a simple gap in astronomical understanding. The earliest attempts focused on measurement errors and observational biases. Perhaps galaxy surveys were incomplete in certain directions, or distance measurements contained systematic errors that artificially created apparent emptiness where galaxies actually existed. Dr. John Huckra from Harvard University led extensive verification studies using independent observational techniques and found that the void persisted across all measurement methods. We checked and rechecked using different telescopes, different instruments, different analysis techniques. Huckra noted before his death in 2010, "The emptiness is real, it's not an observational artifact." Computational explanations suggested that improved simulations with higher resolution and more sophisticated physics might reproduce large voids matching our local environment. The illustrious project, which simulated cosmic evolution across a 106 megaparsec cube with unprecedented resolution, incorporated detailed models of gas dynamics, star formation, and feedback processes. Despite this sophistication, the simulations consistently failed to produce voids larger than 300 to 400 million light-years across, while below our void's observed magnitude. Modified dark matter theories proposed that alternative dark matter properties might explain large-scale structure formation differently than standard cold dark matter models predict. Warm dark matter, self-interacting dark matter, and fuzzy dark matter scenarios were all tested as potential explanations for our cosmic environment. Dr. Mark Vogelsberger from MIT performed detailed simulations incorporating these alternative dark matter models and found that while they altered small-scale structure formation, they couldn't explain void formation on the scale of our local emptiness. Dark energy modifications offered another potential explanation. Perhaps dark energy behaved differently in underdense regions, or maybe its properties evolved over cosmic time in ways that enhanced void formation. The Dark Energy Survey and Planck satellite observations place tight constraints on dark energy's behavior, ruling out most modifications sufficient to explain large void formation while remaining consistent with other cosmological observations. Modified gravity theories, which attempt to explain cosmic acceleration without invoking dark energy, faced similar constraints. Theories including FR gravity, scalar tensor models, and extra-dimensional scenarios all struggled to reproduce both cosmic acceleration and large void formation simultaneously. Dr. Mustafa Ishak from the University of Texas at Dallas tested numerous modified gravity models and found that those capable of creating large voids typically predicted observable signatures that conflict with precision cosmological measurements. Primordial origin explanations suggested that our void resulted from unusual initial conditions in the early universe rather than later evolutionary processes. Perhaps cosmic inflation created larger density fluctuations than standard models. Predict, or maybe phase transitions during cosmic evolution left imprints that evolved into large-scale structure. However, cosmic microwave background observations severely constrain primordial density fluctuations, ruling out initial conditions extreme enough to create voids of our magnitude through standard evolution. Topological defect theories proposed that cosmic strings, domain walls, or other exotic structures from early universe phase transitions might create large-scale underdensities through their gravitational effects. Dr. Tamay Vashespati from Arizona State University developed detailed models of how cosmic strings might evacuate matter from large regions. But these scenarios predict observational signatures, gravitational wave backgrounds, cosmic microwave background distortions, galaxy alignment patterns that remain undetected despite increasingly sensitive searches. Non-Gaussian initial condition models suggested that departures from standard Gaussian statistics might explain large-scale structure anomalies, including our void. These models invoke non-trivial physics during inflation or alternative scenarios for early universe evolution. However, Planck satellite observations place extremely tight constraints on non-Gaussianity, ruling out deviations large enough to explain our void while remaining consistent with cosmic microwave background measurements. Back reaction theories propose that small-scale inhomogeneities might affect cosmic evolution in ways that standard models neglect, potentially explaining apparent cosmic acceleration and large-scale structure anomalies through purely gravitational effects. Dr. Thomas Butchert from the University of Lyon developed mathematical frameworks for averaging Einstein's equations over inhomogeneous distributions of matter, but numerical studies consistently show that back reaction effects remain too small to explain either cosmic acceleration or large void formation on observed scales. Void in void models suggested that our local emptiness might result from multiple smaller voids merging over cosmic time. This hierarchical formation scenario could potentially explain large final void sizes while starting from less extreme initial conditions. However, detailed simulations of void evolution show that merging processes typically create irregular, asymmetric structures with significant substructure characteristics, absent from our local environment's remarkably smooth and spherical geometry. Quintessence and phantom dark energy models, which allow dark energy's properties to evolve over cosmic time, offered potential explanations for enhanced void formation during specific cosmic epochs. These scenarios invoke scalar fields with unusual potentials or coupling to matter that could affect structure formation differently than cosmological constant models predict. Observational constraints from supernova, cosmic microwave background, and baryon acoustic oscillations severely limit allowable quintessence evolution, ruling out scenarios capable of explaining large void formation. Environmental explanations suggested that our void represents a rare but natural configuration within cosmic structure formation that occurs occasionally without requiring new physics. Statistical analysis could potentially explain our presence within such a structure through anthropic selection. Conscious observers naturally find themselves in cosmic environments capable of supporting biological evolution regardless of statistical probability. However, detailed calculations show that even anthropically selected environments shouldn't be as extreme as our observed cosmic address. Multiverse theories proposed that our void represents evidence for interactions between different universes or different regions of an infinitely large cosmos. Eternal inflation scenarios predict infinite cosmic volumes containing all possible configurations of matter and energy, making even extremely unlikely structures like our void inevitable somewhere. While mathematically consistent, these scenarios make no specific testable predictions and require assumptions that extend far beyond empirically accessible science. Observational selection effects offered another category of explanations, suggesting that conscious observers necessarily emerge in cosmic environments with specific properties that appear unusual when viewed from theoretical perspectives that don't account for observer bias. If complex life requires stable galactic evolution over cosmic timescales, then intelligent observers would preferentially emerge in cosmic locations that support such stability, regardless of their statistical typicality within cosmic structure as a whole. Recent attempts involving machine learning and artificial intelligence have applied pattern recognition algorithms trained on cosmological simulations to search for non-obvious formation mechanisms that might explain large void formation. These approaches consistently fail to identify plausible physical scenarios that reproduce our void's properties while remaining consistent with other cosmological observations and theoretical constraints. The systematic failure of explanatory attempts suggests that our cosmic void represents something more fundamental than a simple extension or modification of current theoretical frameworks. Each proposed solution addresses some aspects of the observational puzzle while creating new problems or requiring assumptions that lack independent theoretical motivation or empirical support. Perhaps most troubling is the possibility that our current theoretical paradigms are fundamentally inadequate for understanding cosmic structure on the largest scales. If the same physics that successfully explains cosmic evolution on smaller scales completely fails to account for our immediate cosmic environment, then astronomy might be approaching a revolutionary transition, comparable to the development of quantum mechanics or relativity. This explanatory failure suggests that understanding our cosmic void might require abandoning comfortable assumptions about cosmic evolution and embracing possibilities that extend far beyond the boundaries of current scientific consensus, a prospect that leads to fundamental questions about the nature of cosmic structure itself. Chapter 5. Hidden Physics. The complete failure of conventional explanations to account for our cosmic void has forced astronomers to consider a disturbing possibility. The universe might operate according to physical principles that remain completely hidden from scientific understanding despite decades of theoretical development and observational refinement. This hidden physics wouldn't represent minor modifications to established theories, but fundamental new aspects of reality that become apparent only on the largest cosmic scales, or under the most extreme conditions. The mathematical elegance of physics often reveals itself through symmetries, conservation laws, and unified descriptions of apparently disparate phenomena. Yet our cosmic void exhibits properties that seem to violate this elegant mathematical structure. Its formation requires initial conditions so finely tuned in evolution so precisely orchestrated that they suggest underlying organizational principles that extend beyond gravitational attraction, quantum mechanics, and thermodynamic equilibration. Dr. Giovanni Amelino Camiglia from Sapienza University of Rome has developed theoretical frameworks exploring whether space-time itself might possess discrete rather than continuous structure on the largest cosmic scales. These quantum gravity phenomenology models suggest that space-time discreteness could affect cosmic structure formation in ways that become apparent only across distances comparable to our void's magnitude. While speculative, such scenarios offer potential explanations for why conventional field equations fail to reproduce extremely large-scale cosmic structures. The possibility that cosmic structure formation involves non-local correlations connections between widely separated regions that operate instantaneously across cosmic distances represents another avenue for hidden physics exploration. Quantum mechanics demonstrates non-local correlations on microscopic scales through entanglement phenomena. Theoretical extensions of quantum mechanics to cosmic scales might create correlations that coordinate matter distribution across regions larger than light could traverse since the Big Bang. Dr. Anthony Valentini from Clemson University has investigated whether violations of quantum mechanical predictions might occur under extreme conditions that would affect cosmic structure formation. His de Broglie-Baum interpretations of quantum mechanics allow for subtle departures from standard quantum predictions that could accumulate over cosmic time and distance scales to produce large-scale effects invisible in laboratory experiments, but potentially significant for cosmic evolution. Extra-dimensional scenarios offer another framework for hidden physics that might explain our cosmic void through gravitational influences from spatial dimensions beyond the three we directly observe. String theory and its extensions predict that gravity might leak into extra dimensions on large scales, weakening gravitational attraction in ways that could affect cosmic structure formation differently than Einstein's general relativity predicts in four-dimensional spacetime. Recent theoretical work by Dr. Lisa Randall from Harvard University explores how extra dimensions with specific geometric properties might create gravitational effects that mimic our void's observed characteristics. These scenarios predict subtle deviations from inverse square gravitational attraction on cosmic scales that could explain both cosmic acceleration and large void formation through purely gravitational physics without requiring dark energy or exotic matter. The holographic principle, which emerges from black hole thermodynamics and string theory, suggests that all information within a cosmic volume might be encoded on its boundary surface. If cosmic structure formation involves holographic information processing, then the evolution of large-scale structure might follow principles more similar to computation than traditional physical evolution. Our void might represent a cosmic information processing artifact rather than a conventional gravitational structure. Dr. Eric Verlinde from the University of Amsterdam has developed emergent gravity theory suggesting that gravitational attraction might arise from underlying thermodynamic and information theoretic processes rather than representing a fundamental force. In these frameworks, cosmic structure formation involves entropy optimization and information organization that could create large-scale patterns fundamentally different from those predicted by conventional gravitational collapse models. Consciousness-related physics represents perhaps the most radical possibility for hidden physics that might explain our cosmic void. If quantum measurement involves conscious observation in fundamental ways, then the emergence of consciousness within our local group might have influenced cosmic structure formation through quantum mechanical effects that accumulated over cosmic time. While speculative, such scenarios offer potential explanations for why conscious observers find themselves in such statistically improbable cosmic environments. The possibility that physical constants might vary across cosmic space and time offers another avenue for hidden physics exploration. While laboratory measurements show remarkable constancy for fundamental parameters like the fine structure constant and gravitational coupling, these measurements sample only tiny cosmic volumes over brief time periods. Variations too subtle to detect locally might accumulate over cosmic scales to affect structure formation in ways that could explain our void's properties. Dr. Joe Maguio from Imperial College London has developed varying speed of light cosmologies that allow fundamental constants to evolve over cosmic time in ways that could affect structure formation. These scenarios predict that cosmic evolution might have proceeded differently during specific epochs, potentially creating large-scale structures that appear anomalous when analyzed using current values of physical constants. Dark sector physics interactions between dark matter and previously unknown particles or forces represents another frontier for hidden physics relevant to cosmic structure formation. While dark matter appears to interact gravitationally with ordinary matter, it might participate in complex dark sector interactions that affect its distribution and evolution in ways that become apparent only on the largest cosmic scales. Theoretical models involving dark photons, dark magnetic fields, and dark plasma physics could potentially explain why dark matter distribution in cosmic voids differs from conventional predictions. Dr. David Kaplan from Johns Hopkins University has developed models where dark matter experiences long-range forces through dark sector interactions that could coordinate its behavior across cosmic distances in ways that conventional n-body simulations failed to capture. The anthropic multiverse represents perhaps the most radical framework for hidden physics that might explain our cosmic void through selection effects, operating across infinite cosmic volumes. If cosmic evolution produces all possible configurations of matter and energy across sufficient space and time, then even extremely unlikely structures like our void become inevitable somewhere. Conscious observers naturally emerge in cosmic environments, capable of supporting complex evolution regardless of their statistical typicality. Recent theoretical work on the string landscape, the enormous number of possible vacuum states predicted by string theory suggests that different regions of space might operate according to different effective physical laws depending on which vacuum state they occupy. Our void might represent a region where effective physics differs subtly but significantly from the physics that operates in typical cosmic environments. Information theoretic approaches to cosmology suggest that cosmic evolution might involve fundamental information processing rather than purely physical processes. If the universe operates as a vast computational system, then cosmic structure formation might follow algorithmic rules that create patterns fundamentally different from those predicted by conventional physical evolution. Our void might represent a cosmic computational artifact rather than a gravitational structure. The possibility that cosmic structure formation involves retrocausal influences effects that propagate backward in time represents another exotic avenue for hidden physics exploration. While seemingly impossible according to conventional physics, certain interpretations of quantum mechanics allow for subtle retrocausal effects that might accumulate over cosmic timescales to influence structure formation in ways that appear acausal when analyzed using conventional temporal evolution. Each of these hidden physics scenarios remains highly speculative and faces significant theoretical and observational challenges. However, the systematic failure of conventional physics to explain our cosmic void suggests that understanding cosmic structure formation might require embracing possibilities that extend far beyond current scientific paradigms. The exploration of hidden physics possibilities reveals that our cosmic void might be attempting to communicate something profound about the nature of reality itself, something that requires abandoning comfortable assumptions about physical law and embracing the possibility that the universe operates according to principles that transcend current scientific understanding. This brings us to perhaps the most unsettling aspect of our cosmic mystery: how our impossible void affects fundamental astronomical observations and measurements. Chapter 6: Observational Crisis Hour. Cosmic void doesn't just challenge theoretical understanding. It creates systematic measurement problems that undermine the observational foundations of modern cosmology. Every fundamental parameter that astronomers use to understand the universe, from cosmic expansion rates to dark energy densities, might be systematically biased by our location within an environment so unusual that it skews observations in ways that invalidate decades of careful measurement and analysis. The most immediate crisis involves cosmic expansion measurements. When astronomers observe distant supernova to determine how fast the universe is expanding, they assume their observations represent typical cosmic conditions. However, within our underdense void, space expands roughly 7 to 10% faster than cosmic averages due to reduced gravitational deceleration from surrounding matter. This creates systematic bias in local expansion measurements that could explain the persistent disagreement between different methods for measuring cosmic expansion rates. Dr. Adam Rees from Johns Hopkins University, who won the Nobel Prize for discovering cosmic acceleration, has measured local expansion rates using Cepheid variables and type Ia supernova with extraordinary precision. His measurements consistently show expansion rates of approximately 73 kilometers per second per megaparsec. However, the Planck satellite's measurements of the cosmic microwave background predict expansion rates of only 67 kilometers per second per megaparsec, a discrepancy that has persisted despite increasingly precise observations using both methods. The void hypothesis offers a natural explanation for this Hubble tension. If local measurements are systematically biased by our unusual cosmic environment, then the disagreement doesn't represent measurement error, but rather reflects the difference between local and global cosmic expansion rates. Resolving this bias requires understanding exactly how void environments affect distance measurements, a challenge that pushes observational astronomy to its theoretical and practical limits. Dr. Wendy Friedman from the University of Chicago has led independent measurements of cosmic expansion using alternative distance indicators, including red giant branch stars and tip of the red giant branch methods. These techniques show expansion rates intermediate between supernova and cosmic microwave background measurements, suggesting systematic effects that depend on the specific measurement method and cosmic distance range. Within void environments, each distance indicator might be affected differently by environmental factors that remain poorly understood. The crisis extends beyond expansion measurements to include fundamental parameters of cosmic evolution. Dark energy's apparent properties might be systematically biased by void observations that don't represent typical cosmic conditions. If dark energy behaves differently in underdense environments, either because its intrinsic properties vary or because gravitational effects alter its observable consequences, then current estimates of dark energy density, equation of state, and evolution might require significant revision. Gravitational lensing measurements face similar systematic challenges within void environments. When astronomers observe distant galaxies whose light has been bent by intervening matter, they typically assume the lensing mass distribution represents typical cosmic density. However, Void environments contain significantly less dark matter than cosmic averages, reducing gravitational lensing effects in ways that could systematically bias measurements of cosmic geometry, dark matter distribution, and cosmic distances. Dr. Catherine Haymans from Edinburgh University leads the Kilo-degree survey, which maps dark matter distribution across large cosmic volumes using weak gravitational lensing. Her measurements reveal the cosmic shear, the systematic distortion of galaxy images by intervening dark matter. Shows subtle but persistent deviations in regions that appear to correspond to large cosmic voids. These deviations suggest that void environments affect gravitational lensing in ways that current theoretical models don't adequately account for. The cosmic microwave background itself might be systematically affected by our void environment through mechanisms that remain poorly understood. Light from the cosmic microwave background has traveled through nearly 14 billion years of cosmic space, including the last 2 billion light-years through our local void. This journey through underdense space might systematically affect temperature measurements in ways that could bias fundamental cosmological parameters, including cosmic curvature, dark matter density, and primordial fluctuation. Properties. Recent analyses by Dr. Sabir Sarkar from Oxford University suggest that cosmic microwave background temperature measurements show subtle correlations with local cosmic structure that might indicate systematic effects from our void environment. If confirmed, these correlations would require reanalyzing cosmic microwave background data to account for local environmental effects, a task that could alter fundamental cosmological parameters by amounts comparable to their current measurement uncertainties. Supernova observations face additional systematic challenges beyond simple expansion rate measurements. Type as a supernova, which serve as standard candles for cosmic distance measurements, might behave differently in void environments where stellar evolution occurs under reduced external pressure and altered chemical abundances. The progenitor stellar populations that create Type E as supernova evolve differently in cosmic voids, potentially affecting supernova brightness, color evolution, and light curve properties in ways that introduce systematic biases into distance measurements. Dr. Dan Skolnick from Duke University has analyzed thousands of supernova observations for evidence of environmental effects on supernova properties. His studies reveal subtle correlations between supernova characteristics and local cosmic environment that suggest systematic effects of the magnitude needed to explain expansion rate discrepancies. However, these environmental effects remain poorly understood and difficult to correct, without detailed theoretical models for how void environments affect stellar evolution and supernova physics. The measurement crisis extends to cosmic age determinations as well. Astronomers calculate the universe's age by combining expansion rate measurements with models of cosmic evolution, but both components might be systematically biased by void observations. If local expansion rates exceed cosmic averages and cosmic evolution models don't account for void effects, then age estimates could be systematically incorrect by amounts comparable to current measurement. Precision. Stellar age measurements provide independent constraints on cosmic age through observations of the oldest star clusters. But these measurements might also be systematically affected by void environments. Stars form from gas with chemical compositions that evolve differently in cosmic voids compared to typical cosmic regions. These compositional differences affect stellar evolution timescales and could systematically bias stellar age estimates in directions that either support or contradict cosmic age measurements depending on the specific effects involved. Perhaps most troubling is the possibility that fundamental constants of nature might not be constant within void environments. The fine structure constant gravitational coupling strength, and other parameters that define physical law might vary slightly across cosmic space in ways that become detectable only through precision measurements across cosmic distances. Laboratory measurements sample only tiny cosmic volumes and brief time periods, potentially missing variations that affect cosmic structure and evolution on large scales. Dr. John Webb from the University of New South Wales has spent decades searching for evidence of varying fundamental constants using observations of distant quasars. His most recent analyses suggest subtle variations in the fine structure constant that correlate with cosmic structure in ways that might indicate genuine spatial variation rather than systematic observational effects. If fundamental constants vary across cosmic voids, then every measurement of cosmic structure and evolution might need recalibration to account for local environmental effects. The systematic nature of these observational challenges suggests that modern cosmology might be fundamentally biased by our unusual cosmic location in ways that affect every major measurement and theoretical conclusion. Resolving these biases requires understanding void physics with precision that exceeds current theoretical and observational capabilities, creating a circular problem where accurate cosmology requires understanding our void environment, while understanding our void requires accurate cosmology. The observational crisis has forced astronomers to confront uncomfortable questions about the reliability of cosmic measurements and the validity of theoretical conclusions based on observations taken from within extremely atypical cosmic environment. If our location systematically biases every fundamental measurement, then decades of cosmological progress might need re-examination and potential revision. This systematic measurement bias leads to perhaps the most unsettling implication of our cosmic address, the possibility that we're studying the universe from the worst possible location for understanding cosmic reality. Chapter 7. Measurement Paradox. The most disturbing aspect of our cosmic void location might be its systematic effects on fundamental measurements that form the empirical foundation of modern astronomy. Every observation we make, every parameter we measure, and every conclusion we draw about cosmic reality emerges from this singular perspective within an extraordinarily unusual cosmic environment. The result is a measurement paradox where our most sophisticated observational techniques might be systematically deceiving us about the universe's fundamental properties. Consider the magnitude of this problem. Astronomers have spent over a century developing precision measurement techniques that can determine cosmic distances to within 1%, expansion rates to within 2%, and fundamental cosmic parameters to within 5%. These achievements represent extraordinary technical sophistication and careful systematic error analysis. Yet if our cosmic location systematically biases every measurement by even small amounts, then all this precision might be accurately measuring the wrong cosmic properties. The cosmic distance ladder, the nested series of measurement techniques that allows astronomers to determine distances across cosmic space, faces systematic challenges at every level within void environments. Parallax measurements of nearby stars might be affected by gravitational lensing from local dark matter distribution that differs from typical cosmic densities. Quantified variable star distances could be systematically biased by metallicity effects that result from altered chemical evolution in void galaxies. Surface brightness fluctuation measurements might be affected by stellar population differences that emerge from void-specific galactic evolution. Dr. Lucas Macri from Texas A&M University has led efforts to recalibrate cosmic distance Measurements using observations from the Hubble Space Telescope with unprecedented precision. His team's measurements achieve fractional uncertainties below 2% for distances to nearby galaxies. Yet persistent systematic differences between measurement methods suggest environmental effects that remain poorly understood. We can measure cosmic distances with extraordinary precision, Macri notes. But if our cosmic environment systematically affects every measurement technique differently, then high precision doesn't guarantee high accuracy. The measurement paradox extends to time itself. Within our void's reduced gravitational environment, general relativity predicts that time passes slightly faster than in regions of typical cosmic density. This temporal dilation accumulates over cosmic history, potentially affecting age measurements for stellar populations, radioactive decay rates in distant objects, and even the light travel time measurements that form the basis for cosmic distance. Determinations. Dr. Tamara Davis from the University of Queensland has calculated that time dilation. Effects within cosmic voids could accumulate to produce systematic age biases of roughly 0.1% over cosmic time scales. While seemingly negligible, this bias compounds with other systematic effects to create measurement uncertainties that approach the precision limits of modern observational techniques. The possibility that time itself flows differently within our cosmic environment adds another layer of complexity to an already intractable measurement problem. Photometric measurements, determinations of cosmic object brightness, face systematic challenges from reduced extinction by intergalactic dust and gas within void environments. The sparse matter within our cosmic neighborhood provides fewer opportunities for light absorption and scattering during its journey from distant sources to Earth-based detectors. This reduced extinction makes distant objects appear systematically brighter than they would to observers in typical cosmic environments, potentially biasing distance measurements derived from apparent brightness comparisons. The systematic brightening effect varies with wavelength, observation angle, and cosmic distance in ways that depend on the detailed structure of intergalactic medium within our void. Dr. Piero Madao from UC Santa Cruz has modeled how intergalactic absorption affects photometric measurements across different cosmic environments, finding that void observers should expect systematic brightening that varies between 2 to 8% depending on specific observational circumstances and target object properties. Spectroscopic measurements, analyses of light broken into component wavelengths might be systematically affected by Doppler shifts from our void's unusual kinematic environment. If our local group participates in large-scale bulk motion related to void structure, then every redshift measurement includes systematic velocity components that don't represent cosmic expansion. These bulk motions could bias measurements of cosmic expansion rates, peculiar velocity fields, and even fundamental cosmic parameters derived from statistical analyses of galaxy motion. The cosmic microwave background dipole, the systematic temperature variation across the sky caused by our motion through the cosmic rest frame provides evidence for bulk motion that exceeds predictions based on nearby cosmic structure. Dr. Fernando Atrio Barandola from Universidad de Salamanca has analyzed whether this excess motion might result from gravitational influences of large-scale structure associated with our void environment, finding correlations that suggest systematic kinematic effects of uncertain magnitude and origin. Perhaps most troubling is the possibility that quantum mechanical measurement processes themselves might be affected by our cosmic environment in ways that systematically bias observational results. If consciousness plays fundamental roles in quantum measurement, as some interpretations suggest, then the emergence of Consciousness within our unusual cosmic environment might affect measurement outcomes through quantum mechanical feedback effects that accumulate over repeated observations. Modern astronomical observations increasingly rely on sophisticated data processing algorithms that combine information from multiple detectors, observation epochs, and wavelength ranges to extract cosmic information with extraordinary precision. However, these algorithms typically assume that systematic effects are either absent or can be modeled using theoretical understanding of instrumental and environmental biases. If our cosmic location introduces systematic effects that current theories don't predict, then algorithmic bias correction might actually amplify rather than reduce measurement errors. Dr. David Hogg from New York University has developed machine learning approaches to astronomical data analysis that can identify and correct for systematic effects without requiring detailed theoretical models. When applied to cosmological measurements, these algorithms consistently identify residual systematic effects that correlate with large-scale cosmic structure in ways that suggest environmental biases of unknown origin and magnitude. The measurement paradox creates a circular problem for astronomical research. Accurate cosmic measurements require understanding how our void environment affects observational techniques, but understanding our void requires accurate measurements of cosmic structure and evolution. Each attempt to correct for void-related measurement biases requires theoretical models that depend on cosmic parameters that might themselves be biased by void observations, statistical analysis techniques that astronomers use to extract cosmic information from noisy observational data face additional challenges within void environments. These techniques typically assume that measurement errors follow well-understood statistical distributions and that systematic biases can be identified and corrected using theoretical models. However, if void environments introduce systematic effects that don't follow standard statistical patterns or can't be modeled using current theoretical understanding, then statistical analysis might produce highly precise but systematically incorrect results. The possibility that our cosmic location represents the worst possible environment for accurate cosmic measurements creates profound challenges for astronomical methodology. If every observation is systematically biased by environmental effects that remain poorly understood despite decades of research, then the entire empirical foundation of modern cosmology might require fundamental reconsideration. Recent attempts to address the measurement paradox through multi-messenger astronomy combining electromagnetic observations with gravitational waves, neutrinos, and cosmic rays face similar systematic challenges. Each messenger type might be affected differently by void environments, creating systematic discrepancies between measurement techniques that could either reveal environmental effects or introduce new forms of measurement bias depending on detailed physics that remains uncertain. The measurement paradox suggests that resolving our cosmic void mystery might require developing entirely new observational methodologies that can account for systematic environmental effects without requiring detailed theoretical understanding of void physics. This represents a fundamental challenge to scientific methodology that extends far beyond astronomical research into questions about objectivity, measurement theory, and the reliability of empirical knowledge obtained from within unusual observational environments. Understanding the full scope of this measurement crisis leads naturally to perhaps the most profound implication of our cosmic void, what it reveals about the limits of human knowledge and our ability to understand reality from within our unique cosmic perspective. Chapter 8: Scientific Methodology, Our Cosmic void mystery has evolved into something far more profound than an astronomical puzzle. It represents a fundamental challenge to scientific methodology itself. The systematic failure of theoretical predictions, the breakdown of explanatory frameworks, and the potential bias in observational measurements force us to confront uncomfortable questions about the reliability of scientific knowledge when obtained from within extraordinarily unusual circumstances that weren't anticipated by standard methodological assumptions. The scientific method relies on fundamental assumptions about the relationship between theory and observation, the reliability of empirical measurement, and the universality of physical law. These assumptions work well when studying phenomena that can be observed from multiple perspectives, tested under controlled conditions, and compared against theoretical predictions developed independently of observational biases. Our cosmic void challenges each of these methodological foundations in ways that reveal potential limitations of scientific inquiry when applied to unique, unrepeatable phenomena observed from singular perspectives. Dr. Thomas Kuhn's analysis of scientific revolutions provides a framework for understanding how scientific paradigms change when accumulated. Anomalies exceed the explanatory capacity of established theoretical frameworks. The cosmic void mystery exhibits many characteristics of what Kuhn called a crisis science, a period when standard theories fail to explain crucial observations, leading to fundamental reconsideration of basic assumptions and potentially revolutionary theoretical developments. Void mystery demonstrates how observational bias can systematically affect scientific conclusions in ways that remain invisible to researchers operating within biased frameworks. If every measurement we make is systematically affected by our unusual cosmic location, then scientific methodology based on local observations might be fundamentally unreliable for understanding cosmic reality. This creates an epistemological problem that extends beyond astronomy into fundamental questions about knowledge, objectivity, and empirical reliability. Modern astronomy increasingly relies on what philosophers of science call indirect observation, inferring cosmic properties through complex chains of measurement, theoretical modeling, and statistical analysis rather than direct sensory perception. The cosmic distance ladder exemplifies this methodology. Astronomers infer cosmic expansion rates by combining parallax measurements, stellar physics, supernova models, and cosmic evolution theory into integrated frameworks that can determine cosmic properties with remarkable precision. However, if any component of this indirect observation chain is systematically biased by our cosmic environment, then the entire framework might produce highly precise but systematically incorrect results. Dr. Ian Hacking's analysis of scientific observation emphasizes how indirect measurement techniques can amplify small systematic biases into large systematic errors when theoretical assumptions don't account for environmental effects that affect measurement processes. The void mystery also illustrates what philosophers call the problem of induction, the logical difficulty of inferring universal principles from finite observational samples. Astronomers assume that physical laws operate identically throughout cosmic space and time, allowing local measurements to reveal universal cosmic properties. But if our cosmic location represents an extreme statistical outlier, then local observations might not provide representative samples of cosmic phenomena, undermining inductive inference about universal cosmic properties. Dr. Karl Popper's philosophy of scientific falsification faces particular challenges when applied to cosmic void research. Popper argued that scientific theories must make testable predictions that could potentially be falsified by observational evidence. However, Many explanations for a cosmic void make predictions about cosmic scales, time periods, or physical processes that exceed current observational capabilities, making them effectively unfalsifiable despite being scientifically motivated. The systematic failure of theoretical explanations for our cosmic void demonstrates what philosophers call underdetermination situations where available empirical evidence fails to uniquely determine theoretical conclusions. Multiple theoretical frameworks can potentially explain our void's existence, while making different predictions about cosmic evolution, fundamental physics, and observational consequences. Without decisive observational tests, scientists face the uncomfortable prospect of theoretical ambiguity that persists despite sophisticated measurement and analysis. Bayesian approaches to scientific inference, which combine prior theoretical expectations with empirical evidence to determine posterior probability distributions for theoretical parameters, face particular challenges when applied to cosmic void research. If our cosmic location represents an extraordinarily unlikely configuration, then Bayesian analysis might systematically underestimate the probability of theoretical explanations that predict such configurations while overestimating the probability of explanations that predict typical cosmic environments. Dr. Elliott Sober's analysis of scientific evidence emphasizes how background assumptions and theoretical commitments affect the interpretation of observational data. In cosmic void research, different theoretical commitments about cosmic homogeneity, structure formation physics, or observational selection effects lead to dramatically different interpretations of the same observational evidence. This theoretical pluralism undermines the ideal of empirical evidence, providing objective constraints on theoretical development. The cosmic void mystery also demonstrates how technological sophistication can amplify rather than resolve methodological challenges. More precise measurements reveal increasingly subtle discrepancies between theory and observation, while larger surveys uncover statistical patterns that become more difficult to explain as sample sizes increase. Advanced data analysis techniques can identify systematic effects that exceed current theoretical understanding, creating new forms of methodological uncertainty rather than resolving existing ones. Modern big data approaches to astronomy, which apply machine learning and artificial intelligence techniques to massive observational datasets, face their own methodological challenges when studying cosmic voids. These techniques can identify patterns that human researchers would miss, but they often produce results that lack clear physical interpretation or theoretical understanding. If algorithmic pattern recognition reveals systematic effects related to our void environment, interpreting these effects requires theoretical frameworks that might not yet exist. The replication crisis affecting many scientific fields presents additional methodological challenges for cosmic void research. Unlike laboratory experiments, cosmic observations cannot be replicated in the strict sense. We observe the universe from a device, single location during a unique cosmic epoch using instruments that evolve continuously over time. Verification requires independent analyses of the same data or comparable observations using different techniques. But systematic environmental effects might affect all observation methods similarly. Interdisciplinary collaboration between astronomy, particle physics, and theoretical physics has become essential for cosmic void research. But different fields bring different methodological assumptions and standards of evidence that can create productive tension or methodological confusion. Particle physicists require different levels of statistical significance than astronomers, while theoretical physicists often accept mathematical elegance as evidence for theoretical validity in ways that empirical astronomers find insufficient. The cosmic void mystery has also revealed how social and psychological factors affect scientific research in ways that can either facilitate or hinder methodological rigor. The anomalous nature of our cosmic address creates strong motivations for finding conventional explanations that preserve established theoretical frameworks, potentially leading to confirmation bias or selective attention to evidence that supports preferred theoretical conclusions while neglecting evidence that suggests more radical alternatives. Recent developments in open science practices, including public data release, collaborative analysis platforms, and transparent peer review processes, offer potential methodological improvements for cosmic void research. However, these approaches face their own challenges when applied to research that requires sophisticated theoretical understanding, complex data analysis techniques, and interpretation of results that challenge fundamental theoretical assumptions. The interdisciplinary nature of cosmic void research requires developing new methodological approaches that can integrate insights from observational astronomy, theoretical physics, computer simulation, and even philosophy of science. Understanding our cosmic address might require methodological innovations comparable to those that enabled quantum mechanics or molecular biology, new ways of thinking about observation, theory, and evidence that transcend traditional disciplinary boundaries. Perhaps most importantly, the cosmic void mystery suggests that scientific methodology itself might need to evolve to address phenomena that occur on scales, time periods, or under conditions that strain conventional approaches to empirical investigation. If the universe contains unique, unrepeatable phenomena that significantly affect observational perspectives while remaining difficult to understand through controlled experimentation or comparative study, then science might need new methodological frameworks for reliable knowledge acquisition under such challenging circumstances. This methodological crisis leads directly to perhaps the most unsettling possibility raised by our cosmic void, that we might be fundamentally limited in our ability to understand cosmic reality from our singular observational perspective within such an unusual cosmic environment. Chapter 9. Cosmic Implications. The implications of our scientifically inexplicable cosmic void extend far beyond astronomy into fundamental questions about the nature of cosmic structure, the reliability of physical law, and our ability to understand universal reality from within a location that appears to violate every theoretical expectation about cosmic evolution. These implications force us to confront the possibility that the universe operates according to principles that transcend current scientific understanding in ways that become apparent only under the most extreme conditions. If our cosmic void represents evidence for new physics operating on the largest scales, then the implications cascade through every branch of theoretical science. Just as quantum mechanics revealed new physics at microscopic extremes and relativity revealed new physics at high-velocity extremes, cosmic voids might reveal new physics at macroscopic extremes that require entirely new theoretical frameworks to understand. This possibility suggests that our current understanding of cosmic evolution captures only a fraction of the physical principles that govern universal structure and development. The cosmic homogeneity principle, the assumption that the universe appears roughly uniform when viewed from any location on sufficiently large scales, faces fundamental challenges from our void's existence. If cosmic structure varies dramatically on scales approaching our void's magnitude, then the universe might be far less homogeneous than cosmological theory assumes. This heterogeneity would undermine fundamental theoretical assumptions about cosmic evolution while suggesting that universal properties might vary significantly across different cosmic regions. Dr. George Ellis from the University of Cape Town has developed theoretical frameworks for cosmology in inhomogeneous universes that abandoned the homogeneity assumption. His model suggests that if the universe contains large-scale structure variations comparable to our void, then cosmic expansion rates, dark energy effects, and even the effective strength of gravitational interactions might vary across space in ways that fundamentally alter cosmic evolution from theoretical predictions based on homogeneous models. The possibility that physical constants vary across cosmic space represents another profound implication of our void's existence. Laboratory measurements demonstrate remarkable constancy for fundamental parameters over limited spatial and temporal ranges. But these measurements sample only tiny fractions of cosmic space and time. If constants vary on cosmic scales in ways that correlate with large-scale structure, then physics itself might be fundamentally different in our void compared to typical cosmic environments. Recent theoretical work by Dr. Sean Carroll from Caltech explores how quantum field effects might create spatial variation in fundamental constants through mechanisms that operate only on cosmic scales. If vacuum energy fluctuations accumulate coherently across cosmic distances, they might affect the effective values of coupling constants in ways that become detectable only through precision measurements across cosmic structure. Our void's extreme properties might result from such constant variation rather than conventional structure formation processes. The anthropic principle faces new challenges and opportunities when applied to our cosmic void. Traditional anthropic arguments suggest that we observe cosmic properties compatible with biological evolution, because only such properties allow observers to exist. However, our void appears more extreme than necessary for supporting complex life, pushing anthropic explanation beyond its conventional boundaries into territory that approaches fine-tuning arguments or multiverse scenarios. If conscious observers require cosmic environments with specific stability and isolation properties, then the universe might be far more hostile to consciousness than optimistic estimates suggest. Complex life might be confined to the rare cosmic regions that provide billion-year stability, reduced radiation backgrounds, and steady chemical enrichment conditions that appear to occur only in large cosmic voids. This would dramatically reduce estimates of cosmic habitability while providing natural explanations for the apparent absence of detectable alien civilizations. Dr. Milan Hrkovic from the Serbian Academy of Sciences has calculated that if complex life requires void environments like ours, then the number of potentially habitable cosmic locations drops by factors of thousands compared to estimates based on planetary habitability alone. The Fermi paradox, the apparent contradiction between high estimates of alien civilization probability and the absence of detectable alien signals, might find resolution in cosmic geography rather than biology or technology. The implications extend to cosmic destiny and the future of consciousness in an expanding universe. If awareness emerges only in rare cosmic environments like our void, then the cosmic expansion that carries distant galaxies beyond our observational horizon also eliminates potential sites for consciousness development. The universe might be entering an epoch where consciousness becomes increasingly isolated and eventually extinct as cosmic expansion eliminates the environmental conditions necessary for complex life. Within our void, however, the cosmic destiny unfolds differently than in typical cosmic regions. The reduced matter density and enhanced expansion rate accelerate the approach to cosmic heat death while simultaneously providing more stable conditions for technological civilization development. Advanced consciousness might persist longer in void environments where reduced cosmic ray backgrounds and gravitational disturbances create optimal conditions for artificial intelligence, space colonization, or other technological approaches to consciousness preservation. The possibility that our void represents evidence for multiverse physics, interactions between our observable universe and adjacent cosmic regions, offers another category of cosmic implications. If cosmic voids result from gravitational influences of nearby universes or extra-dimensional effects, then our local emptiness might provide indirect evidence for cosmic domains that remain otherwise inaccessible to direct observation. Eternal inflation scenarios predict infinite cosmic volumes containing all possible configurations of matter and energy, making even extremely unlikely structures like our void inevitable somewhere within the larger cosmic ensemble. If we inhabit a rare fluctuation within infinite cosmic space, then our observations reveal more about selection effects and observational bias than about typical cosmic properties, fundamentally altering the relationship between observation and cosmic understanding. The information-theoretic implications of our cosmic void suggest that cosmic structure formation might involve computational processes rather than purely physical evolution. If the universe operates as a vast information processing system, then cosmic voids might represent computational artifacts or information storage regions rather than conventional gravitational structures. This possibility connects cosmic evolution to fundamental questions about the relationship between information, consciousness, and physical reality. Recent theoretical work on digital physics and computational cosmology suggests that cosmic structure might emerge through algorithmic processes that create patterns fundamentally different from those predicted by conventional physical evolution. Our void might represent a cosmic information processing result rather than a gravitational structure, requiring entirely new theoretical frameworks that integrate physics with computation and information theory. The implications for fundamental physics extend to the nature of spacetime itself. If cosmic voids affect the geometric properties of spacetime in ways that alter the behavior of matter and energy, then general relativity might provide only an approximate description of gravitational physics that breaks down under extreme conditions like those present in our void. This could require developing new theories of gravity that reduce to Einstein's equations under typical conditions while predicting novel effects in extreme cosmic environments. Perhaps most profoundly, our cosmic void might represent evidence that the universe possesses purpose or direction in ways that transcend purely physical evolution. If cosmic structure formation exhibits organizational principles that create optimal conditions for consciousness development regardless of statistical probability, then cosmic evolution might involve teleological elements that guide development toward complexity and awareness rather than following purely random physical processes. This possibility connects cosmic void research to fundamental questions about the relationship between matter and mind, physical law and cosmic purpose, statistical evolution and directed development. If consciousness plays fundamental roles in cosmic evolution rather than representing an accidental byproduct of random physical processes, then our cosmic address might reflect deeper principles that govern the relationship between awareness and cosmic structure. These cosmic implications force us to confront the possibility that our scientific understanding of the universe remains fundamentally incomplete despite centuries of theoretical and observational progress. A humbling recognition that leads to profound questions about knowledge, reality, and our place within cosmic structures that exceed our current ability to comprehend.